Hey, you 12s! Thanks for coming along, guys. I'll post the YouTube video link on the Google Meet chat as well. I think that's probably worthwhile doing. Oh, that's not what. Ignore that. Ignore that. Being an idiot. Being an idiot. I've just posted the learning objectives. Lol. There you go. I was making this during the holiday and almost done with it. Something like this before I thought you would like it. Ooh, Lara's made something for GCSE. I like it. Right. I'll open up the YouTube video as well. And now I'll pop out the chat. I'll pause that and then get rid of it. Sorry, guys. Totally stuffed that up then. I've got to keep my StreamYard thing open, and I keep forgetting sometimes. I do apologize. Can you do me a favor? Can you just give me a heads up on the chat window as to whether or not you can see me okay? I'll share my screen. Let's crack on. And then I'll split it onto this one, and then I'll alter my camera settings. So camera, I'll switch to my clip cam, thanks to Harry. Thanks, Harry. There we go. We're running. So today's lesson is polar. Am I polar or non-polar? That is the question. I'm such a nerd. There we go. So polar or non-polar? This is the question. So 4 learning objectives today, guys. So we can see you. Amazing. So we've got understand polar covalent bonds. Now, I'll flip my tablet. I'm sorry, by the way, every time I flip the tablet, every now and again, the crackling sound happens because of the terrible cables I've got. Let me know if you can still hear me okay. I'm now in tablet mode. So polar or non-polar bonds. We actually can already do this. Based on our knowledge from last lesson on electronegativity, we now should understand when a polar covalent bond occurs. We should be able to already do this one, but we'll do a bit of revision on this in today's lesson. The next one is be able to label them. I think that sounds very reasonable. We should be able to do that one as well. And then we need to talk about symmetry and then identifying polar and non-polar molecules. So those are my learning objectives today. So I'm actually taking this this lesson. It is primarily based on the last learning objective. So what we need to do is we need to apply our understanding of last lesson. So first thing I'd like to do is reminder of electronegativity values. You are expected, you're not really expected to know them, but you should know them. This is important. And the key thing is to realize fluorine is 4. She is the most electronegative of all the elements on the table. And as you move away 1 step from her, you will drop by 0.5. You can't move diagonally, by the way. If you want to get to sulfur, so just to show you sulfur, if I wanted to get to sulfur as a, for its electronegativity value, I start at 4, I'm going to hop to oxygen at 3.5, and then a hop to sulfur being 3. That's how you do this. You can't move in a diagonal way. You've got to move stepwise left. You're moving a bit like a rook in chess is. So it's just nice for me to say, okay, so let's just list a few people of interest. Fluorine, chlorine, bromine, iodine, oxygen, carbon. I'll actually put them in order. Oxygen, nitrogen, carbon, hydrogen. These are the guys of the most important. So this is 4. Chlorine is 1 step away at 3.5. Bromine is then another step away at 3. Iodine is 2.5. Oxygen, where's oxygen? Oxygen is 1 step away, so that's 3.5. Nitrogen's 2 steps away, so that's at 3 as well. And then carbon is, for me to get to carbon then, so 3.5 then to 3, and then 2.5 then, 2.5 for carbon. And then hydrogen's on oddity at 2.2. That's the number you've got to remember. You've got to learn him as well. These two are actually super important. Learn these two. Yeah. And there's a reason why, and you're going to see that today. So now that we've got our data, we need to start looking at molecules. So let's now have a look at methane. It's the first one to mention here. So methane, so two questions we're going to be asking throughout this entire question. We're going to, throughout this entire lesson. Question number 1, polar bonds, question mark? Question number 2 is polar molecule, question mark? Those are now my two questions that I have to ask at every stage. So for methane, the answers to the first question, so answer number 1 is going to be no. There are no polar bonds. We know a polar bond is a bond where the atoms have a difference in Electroneg greater than 0.4. So in this particular example, the carbon-hydrogen bond is 2.5 and 2.2, so the difference is 2.3. So difference is 0.3. So this is non-polar. Yeah. Now, since there are no other bonds in this molecule, that means that this molecule, answer number 2, will be non-polar. This is a non-polar molecule because there are no bonds that are polar. So by the way, I cannot stress the importance of this. This is a nota bene. Carbon-hydrogen bonds are non-polar. You need to know that, folks. It's important. Right, let's go to example number 2. Example number 2. Let's go for this guy. Let's go for chloromethane. Okay. Question number 1. Do I have a polar bond? Well, I now realize that I can ignore the carbon hydrogens immediately. I just blanket know they're non-polar. But I have another bond here. And carbon is 2.5 and chlorine is 3.5. This bond, so carbon-chlorine bond, is polar. And now I can label it. So if I'm now going to label it, because we know that chlorine is higher, this is slightly positive and the chlorine will be left slightly negative. And this is your next nota bene. The atom with the higher Electroneg will be slightly, but it's a delta, slightly negative. Yeah, that's so important. Yeah, I like it. So we can now label our molecule. Slightly positive and slightly negative. The next thing is question number 2. Is this molecule polar? So answer number 2 is yes. The reason being is that the molecule is not symmetrical. And I'll explain that now. So the answer is yes, due to polar bond, but non-symmetrical. I'm going to show you a symmetrical one in a second. Non-symmetrical molecule. So it is going to be polar. I've suddenly realized there's another learning objective I need for this, which is practical evidence. No practical, well, it's actually a demonstration. Demo proof. Okay, I'll come to that in a minute. So we've got chloromethane. Let's go for the next one. Let's go for the example number 3. Okay, let's try this one. Carbon dioxide. So question number 1, does it have polar bonds? Answer to question number 1. So I need to look up my values. Carbon is 2.5. Oxygen is 3.5. Yeah, versus this is polar. Yes. Oops. Yes. Contains polar bonds. Contains polar bonds. Question number 2. Is the molecule polar? And the answer is, does anyone want to guess? So on the chat, is carbon dioxide a polar molecule? Yay or nay? Give me a yes or no on the chat, please. Boom. I don't know what the delay's like. It's about 30 seconds, I reckon. I don't want to add in any more delay by saying pause the video. I just want to see people contribute. Harry says yes. Louis says no. Ooh, conflicting answers. Tasneen, nice to meet you, Tasneen. Thank you for coming. No, good answer. I love it when I have people who aren't in our class. It's lovely to have you. Thank you for coming. I hope you find the lesson useful. So I've got 2 for my class, and it's a yes and a no. It's very interesting. Only one of them. Ange says no. Okay. The answer is no. So we need to now explain why. The reason being is no, because the molecule is symmetrical. Symmetrical. Let me explain what that means. So what's happening is, if we draw this molecule out, so carbon dioxide, you actually need to know this guy. The carbon dioxide is linear in its shape. This is its shape. You learn shapes with me after this, by the way. When we get to the end of bonding on covalent, we then drop into shapes of molecules. And this is linear. What that means is the delta plus and delta minus, yeah, that we can label that. Is it because the dipoles cancel each other out? Yes, Harry, it is. They cancel each other out. The distribution of the electrons is even. It is symmetrical on both planes. Yeah? So it's symmetrical in the vertical plane. These 2 sides are equal. And it's symmetrical on the horizontal plane, which means these sides are equal as well. So what the distribution, people often ask me now, what would it look like from an electron cloud perspective? And it would look like this. It would be symmetrical. It will be pulled heavily towards the oxygens because the oxygens are both more electronegative than the carbons. So they're going to get dragged that way, but it's symmetrical. So this is actually a non-polar molecule. Okay, let's look at another one. Okay, so let's go to another example. Let's try this one out for size. What about this guy? So this is tetrachloromethane. So question number 1, folks, on the chat. Does it have polar bonds? Question mark. Question number 2, is the molecule polar? Question mark. On the chat, please. I want just in order. It's a yes and no, no or yes, yes and yes, no and no, whatever you like. 2 answers next to each other, please. What do you think this is going to be? So I'll just hang around and wait now. It's nice to see. So two answers here. Yeah, so has it got polar bonds? Yay or nay? Is the molecule polar? Yay or nay? Yes and no from Tasneen. Can I just call you Tas? Is that okay? I hope you don't mind that. Ange says 1 yes, question mark. Louis says yes, no. Harry says yes, no. It's lovely to see. Well done, Yi Hearn. Well done to those people. Sure. Thanks, Tas. Nice to see you. Thanks. So, by the way, well done to those people. So we've got yes, it contains polar bonds. Yeah, we know that the carbon is 2.5 and the chlorine is 3.5. So I can now label this as slightly negative and slightly positive. but the molecule is non-polar because it is symmetrical on both planes. Isn't that lovely? Gotta love it. Yeah, I like it. Polar bonds, yes. Polar molecule, no. Love that. Tetrachloromethane. Let's try another one. I love this game. Such a fun game. Let's try this one out for size. What about this one? This is trichlorofluoromethane. So answer question number 1. Do I have polar bonds? Answer number 2. Am I a polar molecule? Go. Try that one out for size. And then followed his answer with no. But try to put them together. I liked the pairing. It was a good way of doing it. Let's see how we get on that. I love this. Harry, yes and yes. This is working well. The delay doesn't seem too bad today. Yes and yes from Tass. Yes, and look at this. I'm loving it. As a teacher, it's always so lovely when everyone gives you the same answer. It's always great in chemistry. And the answer is yes and yes. Well done. Yes and yes. And you know what? If I was going to label it just for fun and games, you know, this is going to be massive. This is going to be massive. These are going to be slightly negatives. And it is definitely polar. If we were to draw the electron distribution of this, the whole thing would be really messy. Let's have a go at it. It's going to look a bit like, that. And it's definitely not an even distribution. I love Ant. Yeah. Love it, Ant. It's great. Definitely not an even distribution. Nice thing just to remind ourselves, nota bene, yeah, polar slash polarized, yeah, polarized, an uneven distribution of electrons. And we can definitely see this in this cloud. Yeah, that is not even at all. The chlorine up there, sorry, the chlorine at 3 point, the fluorine's just like, nope, you know, let's be fair. Fluorine's like this. It's ridiculous. Fluorine's going to suck the electrons out of that molecule big time. So yeah, nice. Okay, let's do another one. What about this guy? This is getting, every time we do this, every question we now increase the level of difficulty as we move up. And by the way, I'm deliberately doing what Edexcel do. Yeah, I'm going to be trying to give you questions that will probably make it tricky to see what's going on. So let's try this one out. Let's try this one out. What do you think of that? So answer question, does it have polar bonds? Is it a polar molecule? What about that? Yes and no. Okay, Harry's giving me a yes and no. Yes and no. Well done to you two for being on the ball. Good job. Nice and quick. Yes and no. Definitely contains polar bonds, but the molecule is non-polar. Symmetry on two axes. I like it. Next. What about this? What about that? Well done, Ange. What about this guy? Now, at this point, by the way, I realize I need to actually wait for everybody to contribute before I move on to the next one. Otherwise, I'm going to get conflicting bits here, which is the nightmare. What about that? Do I have polar bonds? Am I polar? Harry, yes and no. Tass, yes and no. The answer is yes and yes. Now, this isn't your fault, folks. This isn't your fault. Let me explain why. The reason being is this molecule isn't actually what you guys think it is. You guys think, when you look at this picture appears flat. I shouldn't use the word flat, by the way. Flat doesn't exist in chemistry. Planar does. However, it is not planar. This is not a flat molecule. So this carbon, whenever you have 4 bonds, you actually have a 3-dimensional structure. This one here, this is called tetrahedral. And I'm going to draw that one like this. This is actually a 3-dimensional shape. And I'm going to show you this now, folks. I'm going to show you some. This is me very first time entering you guys into the world of shapes of molecules. Like I said, I've tricked you here, and I've done it deliberately. Yeah. So if I do shapes of molecules, animation. Let's try that. And then go that one, effect. I'll go for effect. Why not? And what you realize is these aren't actually flat molecules. They have shapes to them. And this is 3-dimensional. So even though, let's do model. Right. 3 bonds, 4 bonds. Right. What you now realize is that this molecule is a 3-dimensional shape. So no matter where I put the chlorines, they're never actually on the exact opposite sides. So it's quite clever, this, because this image that I originally drew, everyone here would agree that that is actually the same as that. And I drew it in a way to make it look like it would be symmetrical. But these two here, these pictures here, everyone in this room would say they're the same. Yeah, they are the same. The reason being is, in reality, the chlorines, and I can actually add chlorines to this, I believe. Real molecule. Real. I want to build one. Let me build one. Let me add something to this. It's not going to let me build it. I want to actually build one. Build shapes. I'm going a bit off piece here, guys, because I want to be able to build you a chloromethane and show you this. Construct online 3D shapes. Yes, please. So this one's a trick because it appears like it's going to be non-polar, but in fact, it will definitely be a polar molecule because the chlorines are never actually going to be on exactly the opposite sides from each other's. It's not working. Oh, that's weird. Oh no. Okay. I'll do my best to draw it. So if I attempt to draw this, so if we put the chlorine at the top here, yeah, and then going back away from us is the other chlorine there, and then coming out at us is the hydrogen, and then this one is in the plane. This one's in the plane with us. Yeah, there we go. And what you realize is the chlorines, no matter where I put them, no matter where I put the chlorine, they're always actually going to be on one particular side. Yeah, they're going to be like on this side. And what that means is there is going to be a polar side to this molecule. And I apologize for the trap. The reason why I do something like this is because they do this on a regular basis. And it's something just to bear in mind. The way I often say to students is, so students often say, how do I recognize this? And I'm going to come to that now. Since shapes can affect ability to spot polarity, often it is easier to look for oddities. And I know this seems oddities. So essentially, here's the rule. So I need to explain this. all the same, all the same, non-polar. Carbon dioxide is an exception to that rule. Yeah. Any odd atoms, probably polar. Probably. As I said, carbon dioxide breaks the first rule. The reason why I say this, so an example being, let's do this guy. So if they're all the same, all of them, non-polar. Polar bonds, yeah, this is answer number 1, polar bonds, yes. Polar molecule, no. As soon as you add in any oddities, yeah, anything, it doesn't matter how many of them really, then it's probably going to be polar. So if we actually go back to this one over here, this one's the tricky one. Because I said to you guys that this one, I've lost it. Where's it gone? This one here. Yes and yes. Hang on. This one, yes and no. So the problem being with these guys is because these have a shape as well, but they're on the opposite side of the molecule to each of them. And because that single bond's in rotation, the distribution will actually be relatively even. You could actually argue that actually could actually be a polar molecule, and it would be very interesting to see it. Yeah, but like I said, because this actually goes a lot further. There's always an extra level to anything in chemistry. And I don't want you to get lost in the really complicated examples. You don't need to. All you need to be able to do is be able to spot the oddities. And that now, by the way, is going to be a flat out yes. Heck yes. Yeah, very polar, in fact. Let's try another one. Let's try another question. Let's try this one on for size. What about this? Ammonia. What about that guy? Is that polar or non-polar? Is that not polar bonds, question mark? And polar molecule, question mark. Go, try that one on for size. Now all of a sudden we need to look up our values. Nitrogen is 3. Nitrogen is 3. Electron of 3. Hydrogen, 2.2. This is where I need to draw a line under the chat, isn't it? Suddenly realize this is going to become complicated because I've got so many yes. So if I do a quick line on the chat, oh, that's weird. It's just put that, what? It just put that onto my opposite screen. What? It's just put my keyboard onto, that's so funny. I'll draw a line. I'll wait for you guys to all to respond at this point. I've got Louis with yes and yes. I think he was the first one now to contribute. So what about this one? Yeah, to everyone else. Does everyone agree with Louis? Do they disagree with Louis? I've drawn it actually to help you guys here. Yeah, this is not flat. Ammonia. Harry says yes, no. Look at the symmetry, Harry. Is it symmetrical on both planes? It's symmetrical through that plane. Yeah, that one it's symmetrical by, but it's not symmetrical through here. So this is yes, yes. Yeah, this is a yes and a yes. We know that the nitrogen has got a very high electronegativity, so this is going to be slightly minus. The hydrogen is going to be left slightly positive, but it's not symmetrical on both planes. So this is actually yes and yes. Yeah, because look at the distribution. The distribution is going to look like this. That is not symmetrical. Yeah, that's what it's going to look like, guys. It's going to be pulling it all down towards the nitrogen. Just to tell you the shape of this as well, ammonia is pyramidal in shape. Looks like this. It's a little pyramid. Anybody's in why it's called pyramidal? Or trigonal pyramidal, sometimes called. There you go, trigonal pyramidal. So the distribution is very, very uneven here. Yeah, the cloud is whoosh onto the nitrogen. So it's very polar. You see why I've got to walk through these questions and why it's important to do this lesson. Lots of teachers actually skip this lesson in the process. are we supposed to know the shapes out of knowledge? Harry, you have to know the names of the base shapes, but then I need to teach you how to build them. So I'll do that in covalent. When we get to the end of intermoleculars, I move straight into shapes, and then I'll teach you how to build your shapes. It's not very complicated, but you do have to know your base shapes. This one, by the way, is called trigonal pyramidal. Trigonal pyramidal. And yes, you have to learn their names. By the way, this is tetrahedral, if you're interested. I'd love to ask Taz. Taz, have you done shapes yet? Have you done shapes? There we go. So this one is very polar. Ammonia is very polar. Let's go for another one. Let's go for another one. What about this? What about this? What about ethanol? Our favorite Friday night molecule. Do I have polar bonds? And you have done shapes. Cool. As my AS exam is in a couple of days, actually. Ooh, Taz. Okay. I should call you Taz rather than Taz. Taz. Do you want to do a shape for me? Do you want to impress me? Right, let's do... need a periodic table. Let's do arsenic. This is just for good luck. Arsenic. Let's do F3. I need a periodic table. 1 minus. Ooh, impress me, Taz. Impress me. Is that right? Is that going to add up? Maybe it needs to be 2 minus. 2 minus. I'll go for 2 minus. Yeah, 2 minus. Go for that. What shape is that going to be? Right. So this is for my year 12s as well. I'll just show you how you create a shape from a formulae. So step number 1 is to find what's called the central atom, and that's AS because it's surrounded by the fluorines, and you find out what group it's in. So it's in group 5, so I'm going to put 5. Then what you do is you add your attachments. So add attachments. So how many attachments do I have? I've got 3 of them, so I'm going to add 3 to it. Then the last stage, so you add attachments, and then you adjust for charge. Adjust for charge. And this here is 2 minus, so I'm going to add 2 electrons on. What I'm actually doing here, year 12, is I'm counting up the number of electrons that are surrounding the central atom. So the total number there is 10. Now what I'm going to do is I'm going to put them into pairs, divided by 2 to give me 5. Now I draw my base shape. Well done, Taz. Good job, trigonal planar. Outstanding. Good job. So we've got arsenic, 1, 2, 3, 4, 5. Your fluorines are going to go around the middle, and your lone pairs go above and below. They cancel out. That is trigonal planar. Bond angles, please, Taz. 120. No change, no distortion. Isn't that fun? I'm very impressed. Good job. Well done. Do you want, I'm tempted to do another one for yeah, well done, 120, spot on. Good job. Let's go back to my lesson. I'm really impressed. Good job. Okay, ethanol, our favorite Friday night molecule. Question number 1, polar bonds, question mark. Answer number 2, polar molecule, question mark. Go. We're nearly done with today's lesson, actually, guys. Just going to check my learning objectives. Symmetry, cool. Identify non, we're doing it. We're nearly there. Demo of proof. Yeah, I'll find the video for that in a second. Doing well. I'm super impressed with your task. Well done. Super impressed. Well done. Isn't ethanol have a polar end and non-polar end? Yes and yes from Harry. Louis, I know that the thing is though, from a molecular perspective, you've got to look at the distribution over the whole thing. So what you can imagine it would be, yeah, it's going to look a bit like that. And I don't know about you, but that does not look symmetrical. That does not look like an even distribution to me. If you actually want to know what it more accurately looks like, it more accurately looks like this. Like that. That's what it more accurately looks like. And Harry, you're absolutely spot on. Yes to the polar bond. And the polar bond that matters is actually this one now. Oxygen's delta negative, H is, there you go. That's the one that now matters, and that's a yes as well. Well done, Harry, spot on. Yeah, and yeah, well done. Tas, now you're gonna really, really impress me. What is the bond angle here, please? Impress me. If you can do that, I'll be well impressed. This is, by the way, for my students, what I've just asked Tas is the shape within a molecule. When you do shapes as individual molecules, and then at the very tail end, you do shapes within molecules. Because this actually, ethanol actually has two shapes within it. You've got tetrahedral surrounding the carbon atoms, and then you have a different shape surrounding the oxygen. So there are actually different bond angles going on here. So, and that's actually, that takes you up to a grade. What? Harry, how have you just gone and done that? Give me a 0.5 and I'll be happy. 100, how do you know it's 104.5, Harry? Tas, it's not 180. It's not. That's why I was doing it. So just to explain what I've just done. So ethanol, yeah, if somebody asks you, because the reason why Tas said, because we did the bond angle for water, Harry, I am so impressed with you. By the way, it's 104.5, but I'm well impressed. So Tas gave me 180 because of this diagram. And that diagram, of course, is not correct. Yeah, it's not accurate. We're just drawing it flat for ease. What we need to do is we would need to actually, if somebody said, what's the bond angle here? We would have to run the same process. Tas, have you ever been shown the process that I'm teaching you right now? Step 1, find the central atom. What group is it in? It's in 6. Right. Step number 2, add on the attachments. How many attachments does oxygen have? It's got 2. Next. Right. Nope. This is such a, Tas, take this method. It's amazing. Oh my God, were you taught the dot and cross method? You want to blow your brains out every time you get a shape question. Kill me now. Step number 3. So the steps in shapes. Shape steps. Number 1, group of central atom. Number 2, add attachments, add number of attachments. Number 3, adjust for charge. I'll give you an example there. If, e.g., if +1, then take away 1. If -2, then add 2. The reason being is we're counting electrons. So if it's +1, then it's lost an electron, so we take that 1 away. If it's negative, it's gained electrons, so we add it on. In this case, there's no charge on the oxygen, so we don't even need to do it. So no adjustment. Total 8/2 to put it into pairs. Step 4, add together, add up total, and divide by 2. Divide by 2. Yeah, and that now gives me 4. Step number 5, draw base shape. Draw base shape. So the base shape for 4 is tetrahedral. Oxygen in the center. 1, 2, 3, 4. Add on your people. I had carbon here going off on the rest of ethanol. Then had the hydrogen here. There's a lone pair, and there's a lone pair. So this is bent. The shape here is bent. Bond angles 104.5. Can't believe Harry remembered that. Man, Harry, you've got an amazing memory. Well done. So 104.5, same as water. Clever game, right? It works so well. Draw base shape. Yeah, draw. So by the way, so the base shape, draw base shape and bond angle. Because the original bond angle for tetrahedral, 1, 2, 3, 4, the original bond angle for that is 109.5. And then step number 6, minus 2.5 for each lone pair, except each lone pair. So in this case, lone pair, scrap it, minus 5, 104.5. And there is a step 7, which is check to see if they cancel. But you don't really need to worry about that. That one's symmetrical when you've got 2 lone pairs. But that is a really good method. It works really well. Can I just point out, it looks really long, and it really isn't. Like, after you get used to doing this, like, you can do this in lightning speed. BrCl2 minus. Let's run it. So we've got group 7, add 2. Oh, add 1, total number 10, divide it by 2, 5. Base shape 1, 2, 3, 4, 5. Put a person in the middle, that's a bromine. The chlorines are going to go opposite each other, and the lone pairs around the middle. It's linear. I know, right? How crazy is that? Done. Yeah, and then, oh, by the way, and at that point, you don't take away the 2.5s because they all cancel. I've given you an awkward one there. Should we try another one? Let's do another one. BrCl3. Let's do that. Oh no, Cl4. Let's do Cl4. Gotta be careful here. I'm building them in my head. 11. Oh no. And then mine. Let's do add 1 plus 1. So we now do group 7. Add your attachments plus 4. Oh, minus 1. 10. Oh, divide it by 2. 5. Base shape 1, 2. Trigonal bipyramidal for those people who are interested. Now what's going to happen here is you've got 4 chlorines, and the chlorines you can technically put them anywhere if you want to, but in reality they're going to go there, and there, and the lone pair goes there. And this is now what's called seesaw. This is a seesaw structure, because if you draw it like this shape is seesaw, Cl there, and then you've got that's coming at you. This one's going away from you. So it's a seesaw. Rocking, yeah. So I gotta eat, starving, thanks, nice. Okay, and the bond angle here, trigonal bipyramidal, is 120 within the plane, and then 90. And then you've got 1 lone pair, minus 2.5 from both. So that's going to be 118.5 and 87.5, I believe. Have I gone and made the wrong 117.5? Oops. There you go. Done. I hope that's helpful for you, Tass. I hope that's helpful. I'm done with my lesson, to be fair. I'll post you guys some questions from papers on these. Most of them are multiple choice. So I'll post these on your homeworks, but I'll leave you be at this stage. It was fun to do a bit of shapes there for Tass. It's nice to incorporate it. I'll be doing them with my kids shortly. I will end my lesson here if I can track down StreamYard. Thank you so much. It's very, very helpful. Oh, you're very, very welcome. Guys, have a nice lunch. I'll see you all soon. Take care. Bye, guys.